All right, let's have a look through some past paper questions. All right, line is a normal to the curve at the point x equal to -1. Find the values of b and k. So first things first, if that line there is a normal, so let's rearrange it. Therefore, we get 3y is equal to minus x minus k. Y is equal to minus x on 3 minus k on 3. So we know that this equation here is normal to the other one. So the gradient of my normal is equal to -1/3. So the gradient of my tangent is equal to +3. So that means at x equal to -1, which is the point in question, dy dx has to equal +3. So dy dx is given by 5x to the 4 plus b. At x equal to -1, I get +5 plus b, and that has to equal 3. Therefore, b equals -2. So we've got the b value. So what else do we know? So we get y equals x to the 5 minus 2x now, and at x equal to -1, I get y equal to -1 plus 2, which is equal to 1. So it goes through the point -1, 1. So my normal line has to go through the same point, which means that x equal to -1, y must be 1. So over here on this equation, so if I substitute the points in for x and y, I get 1 is equal to -1 on 3 minus k on 3. So I get 1 plus 1/3 minus k on 3. I'll take k on 3 across and bring 1 back. So I get positive k on 3 is equal to 1/3 minus 1. K on 3 equals -2 on 3. K is equal to -6 on 3, which equals -2. Therefore, let's write the answers clearly. K equals -2 and B equals -2. Done. Continuing on, the graph of f dash of x is on the right. On the axis below, sketch the graph of f of x. So f dash of x, so that's where f dash of x is 0. Where does f dash of x equal 0? They're at turning points. So if I just do some loose dotted lines here, they're not asymptotes. All I know is that my derivative, my turning point, is along there somewhere. So where is the gradient? Well, the gradient's negative in between. So I need a negative gradient. So negative gradient all the way down. And then at x equal to 3 something, it becomes a positive gradient. And at the point -1 something, it is a positive gradient to the left. So maybe with colours, that corresponds to the blue sections, which I'll fix. If I go red section through here, it's below the axis, so that's where my f dash of x is less than 0, which makes a negative gradient, which is that section there. All right, continue. If g of x is equal to, find the values of x for which g of x is an increasing function. So I need g of x to be increasing. And for a function to be increasing, it means my gradient is positive. So g dash of x is equal to 3x squared minus 18x plus 15. If I take a 3 out the front, Let's find it equal to 0 first. So the 3 becomes irrelevant. So what's that? It's going to be a plus minus 5 minus 1, x minus 5, x minus 1. So my points of interest are at 1 and 5, yeah? So it's a positive cubic. Oops. So 1 and 5 are my points of interest. So all I'm doing this for is, now it's really clear to me whereabouts this gradient is positive. So the gradient is positive here and the gradient is positive there. All right, so therefore I need, it's a set of values x such that x is strictly less than -1 union x is strictly greater than x such that x is strictly greater than +5. So strictly less than is strictly greater than because I want the gradient to be positive. And obviously if the gradient is 0, it's not positive, it's 0. All right, that's the graph of y equals 3x squared plus a, blah, 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 has a normal with that equation. Find the value of a. So again, it's similar to one we did earlier, isn't it? So the gradient of the normal is 1/3. Therefore, the gradient of the tangent is equal to -1. Whoops, -3 or -1 on 1/3. So okay. Let's just keep working through. So dy dx is equal to 6x. So it's the point we're interested in, isn't it, really? So therefore 6s has to equal -3. Therefore, the point I'm interested in is at -1/2. So that's where my normal equation is. So if I put that into my normal equation, if x equals -1/2, y is equal to -1/2 on 3 plus 1, -1/6 plus 1, which is 5/6. So my normal line goes through the point -1/2, 5/6. So that means that's where my function has to go through. So the y value of 5/6 has to equal 3 times -1/2 squared plus a. 5/6 is equal to, well, -1/2 squared is 1/4. So if I make them both 12, so I get 10 on 12 minus 9 on 12 is equal to a, or a is equal to 1/12. That'll do us. All right, another tangent to the curve at the point where it crosses the x-axis at the point A0. Find the value of a. So we've got a tangent to a line, and then we want to find the x-intercept of that line. So let's find the line first. So we need a gradient. Dy dx is equal to -2x plus 5 at x equal to 1. So dy dx will equal 3. Therefore, the tangent line gradient is equal to +3. I need a point the line goes through. X equal to 1, y is equal to -1 plus 5, which equals 4. So the point I'm interested in is a point 1,4. So my tangent line, y minus y1 equals m x minus x1, 3x minus 3, so y equals 3x plus 1. So there's the equation of my tangent. Now I need to know where the x-intercept is. So at y equal to 0, 3x plus 1 equal to 0, so x is equal to -1/3. Therefore, a equals -1/3. All right. Last one, the graph of the function, and it looks a little bit different. We maybe haven't quite looked at this continuity issue here and how it's discontinuous and things like that, but we will get to that. We did a bit last year. There's the function f of x. On the same set of axes, sketch the derivative function. Okay, so this might be a smidgen challenging getting the technicalities right. So let's rub out those things that I've just put on there. So what's the gradient of the line at each of these points? So what we should be able to get, gradient of that line up to -1 is 0. So what we're going to talk about is at the point, whether it's a solid dot or a hollow dot, okay? What about the gradient of this blue section here? Okay, what is it approximately? Well, we don't know exactly, but we know it's positive. So it's positive. So let's put it in, and it's a linear line, so it's positive, and it's the same value all the way along. So what if we just go from there to there? Okay. And what about we'll call it red line here? That looks like a bit of a parabola, doesn't it? But it's 0 at the start, looks like a turning point, and then it increases. So maybe it's got a positive, so it's 0 at the start and increases. Maybe something like that. Now, the interesting in black, what about at the end points? Now, hopefully it sort of makes sense that because that's an open dot there, the gradient is not defined at that point, okay? And because even though this function down here is defined at x equal to 2, when we get to our formal definitions, our derivative, our function needs to be continuous for the derivative to exist. That's one condition. Okay, so since it's not continuous at that point, the derivative doesn't exist at that point. Now, this one here is not differentiable for another reason. Yes, the function is continuous, but at that point of interest there, it's what we call a cusp. And so the derivative of the blue line is different to the derivative of the green line at the point that they meet. Okay, and you can see that where we've sketched it. And because they're not, because we talk about limits, because the derivative of the line as we approach from the left does not equal the derivative of the line as we approach from the right, the derivative doesn't exist. All right, so we've got hollow circles at each of those points, so what I would expect you to be able to get is certainly what sort of a line. The technical side of it, whether it should be hollow or solid, well, that might be a bit more challenging. So let's just get rid of those ones there, just to make life a little bit easier for us. Okay, so that's roughly what it looks like. What is the domain of the function of y equals f dashed of x? Okay, well, that's almost a continuation of that question, isn't it? So we've got x as an element of R, so both of these functions, all of these functions continue. So the domain of f dashed of x, well, it's pretty much R, isn't it? Except for a couple of points, -1 and +2. They're the only 2 points that my derivative isn't defined at. All right, job done.